Hi, so today we're going to discuss an introduction to special relativity, the speed of light, the Michelson-Morley experiment, and Einstein's principle of relativity. So in our everyday experience, the speed of objects is much less than the speed of light, right? But it is possible to accelerate, for example, an electron to a speed of 0.99 c, which is 99% of the speed of light, by using a potential difference of several million volts. But Newtonian mechanics failed to describe the motion of particles with speeds close to that of light. For example, according to Newtonian mechanics, if the potential difference is increased, it should be possible for the electron speed to exceed that of light. But experiments show that the speed of the electron and all other particles in the universe is always less than the speed of light, even if the accelerating voltage is increased. So Newtonian mechanics does not place an upper limit to the speed, and this contradicts the experimental results. So in 1905, Einstein published his special theory of relativity, and this theory represents one of the greatest intellectual achievements of the 20th century, and it turned out that Newtonian mechanics is just a special case of Einstein's theory. So as we shall see here, special relativity predicts the slowing down of clocks and the contraction of lengths in a moving reference frame as measured by a laboratory observer. And this was confirmed by experiment. And this, of course, stretches the human conception of reality beyond everyday experience. Because it shows that what we experience with our senses is only a surface layer of the world, and that there are other layers or levels in which speeds, energy, or frequencies of vibrations or mass is beyond the spectrum of our everyday experience. Also, special relativity leads to the famous mass-energy formula E equal mc squared. So special relativity was used in designing devices that utilize high-speed particles such as particle accelerators, and these devices would not have been able to work if they were designed according to Newtonian mechanics, okay? So if you go back to Newtonian mechanics, it states that Newton's laws are valid in all inertial frames of reference, where an inertial frame of reference is defined as one in which Newton's first law is valid. And I discussed this extensively in my book, and you can find it in the link in the About section, okay? Also, any system moving with a constant velocity with respect to an inertial frame is itself an inertial frame of reference, okay? So there is the principle of Newtonian relativity, which states that the laws of mechanics must be the same in all inertial frames of reference, okay? So for example, let's consider a truck moving with a constant velocity, and suppose the person here throws a ball vertically upwards. So according to this person, the ball follows a vertical path. So for this person, the motion of the ball appears to be the same as if this person was at rest on Earth, right? So here both the surface of the Earth and the system of the moving truck are inertial frames of reference because Newton's first law is valid in both of these frames. So now consider an observer in the Earth frame here, and is observing the motion of the ball thrown by the other person, okay? So for this stationary observer, the path of the ball is parabolic, right? So the ball has, according to this observer, a horizontal component of velocity equal to the velocity of the truck. So although some aspects of the experiment or motion appear different to the two observers, they both agree that Newton's laws are valid, okay, in both inertial frames. So whether the ball is taking a straight path according to the first observer or a parabolic path according to the second. In both cases, the motion follows the same laws and principles, like the conservation of energy or momentum, okay? So, so all inertial frames are equally valid. So there is no preferred reference frame, and a mechanical experiment cannot detect the difference between the two inertial frames. The only thing that can be detected is the relative motion of one frame with respect to the other. So there is no absolute or universal frame of reference that can be used everywhere, okay? So there is no such thing as absolute motion because all constant velocity motion is relative. So we can only detect that there is a relative motion between the two frames, and the question of who is moving is meaningless. So if something is changing its position with respect to us at a constant velocity, the question of is it moving or are we moving is meaningless. The only thing that we can detect is that there is a relative motion between us and that something. So now suppose that we have two inertial frames of reference, S and S dash, and suppose that S dash is moving with a constant relative velocity v, okay, along the x dash axis. So v is the velocity of S dash measured relative to S, okay? And suppose an event occurs at the point P and let the origins of S and S dash coincide at t equals 0. Then an observer in S will describe the event with the space-time coordinates x, y, z, t, and an observer in S dash will describe this same event using the coordinates x dash, y dash, z dash, and t dash. And these coordinates are related by the Galilean transformation given by these equations. So note here that the time is assumed to be the same in both inertial frames, right? In both S and S dash. So according to classical mechanics, all clocks tick or run at the same rate, regardless of the clock velocity. So that the time at which an event occurs for an observer in S is the same time measured for an observer in S dash. And so consequently, the time interval between two successive events should be the same for both observers S and S dash. But it turns out that this assumption is incorrect if the speed v of S dash relative to S is comparable to the speed of light. So let's consider now the Galilean addition law for velocities and suppose that two events are separated by a distance dx and a time of dt as measured by the observer S. So it follows from this equation here that the distance dx dash between the same two events as measured by S dash is given by this equation. And since dt is equal to dt dash, we have this equation here, okay? So, and this gives ux dash is equal to ux minus v, and ux dash and ux are the instantaneous velocities of the object relative to S and S dash respectively. And this is known as the Galilean addition law for velocities or Galilean velocity transformation, and it is only valid when the relative speed v is much less than the speed of light. So in the 1800s, physicists thought that the light needed a medium to move through like other classical waves, and they called this medium the ether, and that the speed of light was only c in an absolute frame that is at rest with respect to the ether. So attempts were made to prove the existence of the ether frame and the Newtonian idea of an absolute frame, okay? And because of the extremely high speed of light, the changes of c plus or minus v will be really small, right? So scientists of the time decided to use the Earth, which moves around the Sun at 30 kilometers per second, as the moving frame to try to detect these small changes of c plus or minus v. So for an observer on Earth, he or she can be considered stationary, and the absolute ether frame, which is the medium for light propagation, will move past the observer on Earth with a speed v, right? So finding the speed of light in this case would be like finding the speed of an aircraft by measuring the speed of the medium, which is air. So it is like imagining an ether wind, okay? So a method to detect this ether wind is to measure its influence on the speed of light using an apparatus that is fixed on the Earth reference frame. So if v is the speed of the ether relative to Earth, then the speed of light should have a value of c plus v when it propagates downwind, like here, and the value of c minus v when it propagates upwind, and it should have some intermediate value when it propagates at some direction to the wind, like in this case. So if the Sun is assumed to be at rest in the ether, the velocity of the ether wind would be equal to the orbital velocity of the Earth around the Sun, right? And this velocity is approximately equal to 3 times 10 to the power 4 meter per second. So since the speed of light is 3 to the times 10 to the power 8 meter per second, it should be possible to detect small changes of the speed of light of about 1 in 10 to the power 4 for upwind or downwind propagation. But as we shall see, all attempts to detect such changes and prove the existence of an absolute ether frame failed, okay? And to understand this further and show why there is no absolute or preferred frame of reference, suppose a light pulse is sent out by an observer S dash standing inside a car moving with a velocity v. So here the observer stationary on Earth is S and the other one is S dash. So the light pulse has a speed of c relative to S dash. And according to Newtonian relativity, the speed of the light pulse relative to the stationary observer S should be c plus v, right? But this is in contradiction to Einstein's theory and experimental results, in which the speed of light is the same for all observers. So to resolve this paradox, either 1, the laws of physics are not the same in all inertial frames, or 2, the Galilean law of addition of 4 velocities is incorrect to apply in this case. And this second alternative proved to be the case. So it is incorrect to apply the Galilean velocity transformation because the speed v is close to the speed of light. And so the notion of absolute time and absolute length that form the basis of the Galilean transformation should be abandoned. So the statement that the laws of physics are the same in all inertial frames of reference forms the first principle of relativity. And this principle follows, as we said, from the absence of a universal frame of reference, because if the laws of physics were different for different observers in relative motion, then the observers could find from these differences which of them is stationary in space and which is moving, okay? But such a distinction does not exist. Also regarding classical theories, note here that, as we said, Newtonian mechanics is a special case of Einstein's relativity. And also Einstein showed that Maxwell's theory is consistent with special relativity, unlike Newtonian mechanics. So we will now discuss the Michelson-Morley experiment, which represents the most famous experiment that was designed to detect small changes in the speed of light, okay? And it was performed in 1887 by Albert Michelson, and it confirmed that the ether hypothesis was not true. And the experiment aim was to measure the velocity of the Earth relative to the ether using Michelson interferometer, shown here. And as you can see, there are two arms. One arm of the interferometer is aligned along the direction of motion of the Earth through space. So the motion of the Earth through the ether is equivalent to the ether flowing past the Earth in the opposite direction with a speed v, as you can see here. And this ether wind in the opposite direction to the Earth's motion should make the measured speed of light relative to the Earth's frame of reference to be c minus v. So c minus v as the light is approaching mirror 2, and to be c plus v after the light is reflected from mirror 2 and moving in the same direction as the wind, okay? So v, as we said, is the speed of the Earth through space, and so it is the speed of the ether wind, and c is the speed of light in the ether frame. So as the two beams of light are reflected from M1 and M2, they recombine and an interference pattern of bright and dark fringes is formed, okay? So if the ether existed, then if this interferometer is rotated through an angle of 90 degrees in the horizontal plane, then this will change the speed of the ether wind along the direction of the arms of the interferometer, right? And this should cause the fringe pattern to shift slightly, but enough to be measurable. But this was never observed in the experiment, and it failed to show any change in the interference pattern. And even after the experiment was repeated many times, still no change in the fringes was observed, and this result contradicts the ether hypothesis. And it showed that it is impossible to measure the absolute velocity of the Earth relative to the ether frame, okay? And this showed that the idea of an ether that permeates all space should be abandoned. Also, since light was shown to be an electromagnetic wave, it required no medium to propagate. So now we will go into more details of the Michelson-Morley experiment. So suppose that the two arms of the interferometer are of equal length L, okay? And the light beam that is traveling along arm 1 is in a direction parallel to the direction of the ether wind, okay? And its speed, according to the hypothesis, should be reduced by the wind blowing in the opposite direction. So the light is approaching M2, and it should have a speed of c minus v relative to the Earth if the ether existed. And after being reflected, it will be moving in the same direction as the ether wind, right? And so the light beam should have a speed of c plus v relative to Earth when it moves along this direction. And so the time of travel to the right is L over c minus v, and the time of travel to the left is L over c plus v. And so the total time of travel for the round trip along this direction is given by this equation, okay? So for arm 2, which is perpendicular to the ether wind, the speed of the beam relative to the Earth is square root of c square minus v square. Then the time of travel for each half of the trip is L over this value. And so the total time of travel for the round trip is 2L over square root of c square minus v square, okay? And so the time difference between the light beam traveling along arm 1 and the beam traveling along 2 is delta t is equal to t1 minus t2, okay? And because v square over c squared is much less than 1, this expression can be simplified by using the binomial expansion here. And so delta t is equal approximately to L v square over c cubed, okay? So these two light beams here, so they start out in phase, and after reflecting they return to form an interference pattern, okay? And the time difference between the arrival of the two light beams at the telescope should give rise to a phase difference between the two beams, resulting in an interference pattern when they combine at the telescope, okay? And the difference in this pattern should be detected when the interferometer is rotated by an angle of 90 degrees in the horizontal plane, such that the two arms exchange positions, okay? And the net time difference in this case after rotation should be double the case before rotation. And so we want to find the path difference that corresponds to this time difference, and it's given by this equation. So delta D is equal to C times 2 delta T equal to 2L V square over C square. And the fringe shift that corresponds to this path difference is equal to the path difference divided by the wavelength of light, okay? So it's delta D over lambda because the change in path length of one wavelength gives a shift in one fringe, okay? So the shift is equal to 2L V square over lambda C square. And in the experiment, each light beam was reflected many times by the mirrors, giving an effective path difference L of 11 meters, okay? So substituting this value and also substituting V, which is 3 times 10 to the power 4 meter per second, which is the speed of the Earth around the Sun, we get this value for the path difference, okay? And this should produce a shift in the fringe pattern that, for example, let's say for lambda equal to 500 nanometers, the shift will be equal approximately to 0.4. And the device used was capable of detecting a shift as small as 0.01 fringe, okay? But no fringe shift was ever detected, and it was concluded that the motion of the Earth with respect to the ether cannot be detected. And then in 1905, Albert Einstein solved the problem with the special theory of relativity. So Einstein based his theory of special relativity based on two postulates. The first one is the principle of relativity, which states that all of the laws of physics are the same in all inertial frames of reference. The second is the constancy of the speed of light, and it states that the speed of light in vacuum has the same value of 3 times 10 to the power 8 meter per second in all inertial frames, regardless of the velocity of the observer or the velocity of the source emitting the light. And as we shall see, this has changed our notion of space and time. So the first postulate represents the generalization of the principle of Newtonian relativity, which we discussed in the previous slides, that only referred to the laws of mechanics, okay? So according to this postulate, the speed of light with respect to a laboratory at rest is the same as speed with respect to a laboratory moving with a constant velocity relative to the laboratory at rest, okay? And so there is no preferred frame, and so there is no absolute or universal frame of reference. So postulate 2 follows from 1 because if the speed of light was not the same in all inertial frames, it would become possible to distinguish between inertial frames and identify a preferred absolute frame, right? Also, this postulate denies the existence of the ether. So the results of Michelson-Morley experiment could be understood based on Einstein's theory of relativity, and the light will be moving at a speed c after reflecting from both mirrors, okay? Not with a speed of c minus v or c plus v as was assumed by the ether hypothesis, but with a speed c. And so the motion of the Earth does not influence the speed of light, and so relative motion is unimportant when measuring the speed of light. So we will now discuss some consequences of special relativity. So as we mentioned before, for a certain event, different observers in different inertial frames describe the same event with different coordinates, okay? And as we shall see in the following slides, the distance between 2 points and the time between two events depend on the frame of reference in which they are measured. And this contradicts with Newtonian mechanics and our everyday experience, okay? Events at different locations that occur simultaneously in one frame of reference are not simultaneous in another frame that is moving uniformly relative to the first frame, okay? So the notion of length, time, and simultaneity are different in relativity than classical physics. So Newtonian mechanics assume the universal timescale that is the same for all observers, okay? And so in Newtonian mechanics, two events that are simultaneous in one frame are also simultaneous in another frame. But according to Einstein's theory of relativity, a time interval measurement depends on the reference frame in which the measurement is made, okay? So to illustrate this, Einstein devised the following thought experiment here. So suppose a boxcar is moving with a uniform velocity v, and two lightning bolts strike its ends as shown here, okay? And as it does, it leaves marks both on the boxcar A dash, B dash, and on the ground A, B, okay? So suppose an observer at O dash moving with the boxcar is at a midway between A dash and B dash. While there is another observer at O on the ground, which is midway between A and B. And suppose the two observers record the two events A and B for O and A dash B dash for O dash. So the two light signals reach the observer at O at the same time. So this observer finds that the light signals traveled equal distances with the same speed. And so this observer here at O concludes that the two events A and B occurred simultaneously, okay? But for the observer O dash, at the time the light has reached observer O dash has moved, right? And the light signal from B dash has already moved past O dash, while the light signal from A dash has not yet reached O dash. And because according to special relativity, observer O dash must measure the same speed of light as that measured by O dash concludes that the event B dash occurred before A dash, okay? And so for O dash, the two events are not simultaneous. And so two events that are simultaneous in one reference frame are in general not simultaneous in another frame, moving relative to the first frame, okay? And this shows that simultaneity is not an absolute concept, but it depends on the relative motion of the observer. And both observers, in this case, are correct when describing the two events, because in relativity there is no preferred inertial frame of reference. And so the consequences of special relativity is that the distance between 2 points and the time interval between two events depend on the frame of reference in which they are measured, okay? And second is that simultaneity is not absolute, but something that depends on the frame of reference, okay? So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.